Hello, my name is Andrew, and my group members for this quarter were Wanru, Kirk, and Tian. So I will start out by introducing our game, Revolutions of Atonement, to you guys. And the basic idea of the game is that the player has to go around this map and rescue various minions that are scattered across the map, and then bring all of them to this goalpost, which represents a safe house on the right side of the map. So then, along the way, there are these two traps that are represented by these these rows of entities, and these two traps will be moving back and forth and will kill any minions that they touch. So in the process of rescuing the minions, the player also has to avoid these traps. So the way we implemented this project was pretty interesting. We had a lot of trouble moving a project from one computer to another. For example, flow graphs and constants in flow graphs and I guess links in flow graphs just wouldn't carry over for whatever reason. So in the end, rather than just fixing all these issues every single time we wanted to move the project, we just kind of all worked together, split up each portion of the project, and then compiled everything together on Tian's computer. So that actually kind of introduced a little issue when we were recording these presentations, because while Tian's computer was by far the most powerful of all of ours, it was also a desktop with no mic. So we recorded all of these recordings in advance and then brought them home to dub over. So if there are any pacing issues that you might find weird, that is just the reason, and just in advance. So another thing is so even though we all work together, I guess, we just each chose a certain portion of our project to present about that we felt most comfortable to talk about with you guys. And one final thing before we start getting down to it is we actually made two versions of our game. So this original level was actually, while the idea seems pretty simple, it proved really complicated to optimize. So we made a stripped down version for AI to do machine learning on. And that will be what Tian will be talking about later. And I'm going to start out by showing you guys the flow graph that we made for our minions' behaviors. Alright, so as we can see here, this is the player level. And the player starts on the left side next to this trident, and we just use the small robot that comes with Lumberyard for our player, and we use these small boxes for our minions. So, as everyone knows and remembers, we have to make Lua scripts for characters in our game, and we made one for the minion. So this minion entity.lua mainly is derived from the rigid body scripts, but we also added some properties and functionalities, including recording when the minion first meets the player and has to start following the player, as well as some functionalities that we didn't end up using in the game, as well as this hide and unhide flow events, which basically when the minion is saved by the safe house or killed by a trap, the minion is hidden. And we used these flow events for that. What we actually found was it was much easier to implement intricate functionalities using smart object rules and flow graphs instead. So we opted to rewrite or remake all of those functionalities and build upon them using this activity flow graph. And in the activity flow graph, we can see it's actually pretty simple, but that is because this is just the top layer. So then this top layer mainly just feeds in the player's ID and the minion's phone ID into this module called stock no oscillation. And what stock no oscillation refers to is a common problem that occurs when following is you'll overshoot the target, and then you'll overshoot again on the opposite direction, and then you'll start oscillating around the target, which is something we didn't want. And then stock no oscillation contains the logic for this, as well as other actions and capabilities of our minion. So it's pretty complicated, I'm not going to lie, but it'll make a lot more sense when I break it down. Here we just set the material for our minions. The minions material is just the default material at first, but what we want to happen is when the player approaches the minion, we want the minion's color to turn to 25500, which is red, and it does this over a time period of 1 second. So then once the minion turns red, it shows that it is going to start following the player. And while there's this cancel node, we don't actually call it from outside of this module because we want the minion to always be following these physical rules that we've written for it. So the rest of this flow graph are just various forces. There's an inside force or inside of range force for when the minion is within a certain range of the player, as well as a damping force and outside force. So then these forces are calculated using the mass from this physics node, and the damping force is basically just a small force to make sure the minion is moving smoothly and not erratically. So all of these calculations are done per tick. So each tick, we calculate these forces and update them for the minion. And then we also calculate the distance between the minion and the player using this less than node. So then first we have to calculate the distance between the minion and the player, which we do over here using these two get position nodes. Again, we get the positions per tick. And into these get position nodes, we feed in the minion's ID as well as the player's or the master's ID. And then after that, we calculate the distance between them over here. The 1.5 is the player's radius, which we add to the distance. And then also here, the 10 is the radius that we want to set for the inside versus outside radius. So if this less than evaluates true, that means the minion is within range, within this set range. And that means, and when the minion is within the range, we just want to stop the minion and make sure it doesn't overshoot. So we slow down the minion, providing stopping force. And then if the minion is out of range, we want it to hurry up and catch up to the player. So we do basically the same thing, but instead of a stopping force, we provide a very large pushing force, so to let the minion catch up to the player. So one thing I also forgot to mention is that these forces were applied only they're isolated to the X and Y plane, and they're not applied to the Z plane, so that the minion won't start just bobbing up and down while it's moving. So now I can show you the end result of that node in action, but let me just turn on debugging just to double check in case there's any errors. And now let's start. So here you can see when we approach the minion jumps up into the air, bobs up and down, and turns red slowly, as I mentioned. So while we're still within range and moving slowly near the minion just follows us slowly and it stops before it reaches our position. So it will never overshoot, and if we're still within range, it moves at a basically constant speed. And once again, when we stop, the minion stops as well. So up to this point, the flow graph's working perfectly, but when we go quickly, that large pushing force came into play, and the minion catches up really quickly as well. And in addition, these damping forces also allow us to let the minions stick together without bouncing all around, bouncing off of each other, which was a problem that we encountered before we added these damping forces.